All right. So this is something I've really been meaning to do for a while, but never got around to it until now. In fact, it might be, I don't want to say it's too late, but maybe not as effective as it once was. But today is a paper review and re-implementation of the paper Variational Quantum Policies for Reinforcement Learning by Jerbi or Jerbi, I don't know, et al. From 2021, March 10th. And so really what this is policy gradient RL with quantum variational circuits. And so the reason I say this might be sort of somewhat obsolete is just because there is a TensorFlow quantum tutorial that, I'll link below and I'll also link the paper, of course. But my implementation does differ, and I still think there's value in it. They do a different style than I do, so we'll see. But yeah, you can also just run their implementation, and that's probably fine. So I'm not going to do a deep dive, on reinforcement learning here. I was thinking about starting a series about all the contemporary implementations of contemporary reinforcement learning algorithms like soft actor critic, TD3, PPO, etc. But I feel like that's kind of been overdone. There's so many resources for all that. But I guess if there is any interest in doing those contemporary algorithms, explaining and implementing in TensorFlow 2, then I guess I could do that. But yeah, so this policy gradient is just a reinforce algorithm. So it's just directly optimizing the policy gradient with no sort of improvements, no, advantages or anything like that. And so, yeah, let's just get into the paper. Let me see if I can share my screen. I have it in a PDF, but it's okay to share. It's just a archive version that I downloaded so I can mark it. So basically, yeah, there's a couple parts to their paper. They propose both raw v raw reinforce and softmax reinforce. And I just implement softmax because it performs better. Also, part of the reason I was so interested in this paper is just because after I wrote the paper on the DQN, which I previously discussed, I immediately, right, that the natural next step was to try reinforce, but I couldn't get it to work no matter what I tried. I even tried sort of custom distribution outputs as opposed to softmax, but I couldn't get it to work. And what I think it is really an encoding problem. But I'll get to that later. So we can skip the introduction, yada, yada, yada. We all are interested in this work. We all assume some knowledge, right, of the reinforcement learning. If you don't know, well, the value, right, is just the sum of discounted rewards. And you can take the gradient of this. Yeah, the gradient of this, right, that's just the optimization. So this is the algorithm we're going to be implementing right here, except the value function approximator will not be differentiable. And so, yeah, so basically you collect a batch, or you go through basically an episode, and then you compute the returns by going, basically stepping back from the last point, and then you can update the parameters using this gradient update. And notice here that we don't do this in the implementation. They don't even do it in the paper. They don't have a value function, a differentiable value function. I don't think, at least. Yeah, you can see here that they talk about the baseline. They might use a baseline, but I don't think they use a learned critic. And so, yeah, going through here now, we can see the circuit ansatz. And so we can see they start off with all Hadamars to create an equal superposition. They have alternating parametrized, well, they're both parametrized, but sort of this is your typical layer, right? And then this is your data re-uploading. This is the re-uploaded layer. And so this is right from the paper I previously re-implemented. This is the idea of using this. So they have the input, right? This is the state. And they multiply it by some learned weights here. And then they repeat this until they measure in the computational basis here, you can see. And so we can see this is a raw VQC. We don't look at that. So yeah, so this is what we care about, the softmax VQE. And so this is fancy, right? This looks all fancy. All this is saying is given some output, some weighted output, right? They take the expectation values and multiply them by some weights. Given this output, just compute a softmax over these expectation values multiplied by the weights, and that's the policy, right? That's pretty standard, right? The softmax is typically how it's done for discrete distributions in deep reinforcement learning. The gradient, right? We all know the fancy stuff about gradients. I do adjoint here because, you know, I'm lazy and I don't want to wait for parameter shift to converge. And we can see here that this is softmax, right? This line does better in all of them. And I'm just doing cartpole here. You can see this is beta 100, but I don't do that. I just do beta equals 1, and that just is sort of a temperature parameter in the softmax distribution. And so, yeah, this is all just different things to consider, different theorems. I don't even know what is going on right now. Let's see. Oh yeah, this is just a sort of it's an interesting section about potential quantum advantages, but it's not relevant to what I'm implementing. So now we can scroll down to the hyperparameters. And so we can see here, we're using cartpole v1, and these are the parameters. So because I'm I'm lazy, right? They have different learning rates for every single, right? They have 3 weights. They have the re-uploaded weights, the standard weights, and the output weights. And I mean, all of those are complicated, right? I don't want to deal with all those hyperparameters. So I just do the average, which would be 0.06 is the average. I just set that as the learning rate for all of them. I also do 0.99. I never like to do 1, just personal preference. Beta equals 1. And batch size, I leave flexible to be whatever the episode length is. And then the depth I also set to be 5. And so we are sort of somewhat faithfully replicating it. I don't want to claim that any of these results I present here are credit or discredit this idea. It's just I'm just trying to stick somewhat at least to the parameters presented. So that's basically the idea, right? The idea is the exact same as I previously discussed. That is using a quantum variational circuit as a function approximator. This time, the difference is that they do data re-uploading. I also included a comparison without re-uploading, and there's some interesting results there. So let's just get into the code implementation. Let me do, oh, weird, can you not see? Let me check. Oh, okay, you can't see. Okay, here we go. So first, let's go over the reinforce algorithm. Zoom in a little. So we have standard imports, gem, matplotlib, all this stuff. And then we have, I don't know why my highlighter isn't really working. So we have our action space and our observation space. We set the gamma to be 0.99. We keep track of our states, actions, rewards. We create our policy, which I'll get to later. And we set the optimizer to be 0.06, as I said. At each episode, right, we remember the states, the actions, and the rewards that we got. Maybe I should just skip down to the actual interaction, right? So we have 300 episodes that we're doing. We consider a 20 rolling average. It's cartpole v1. This is all just setting up the average consideration. So for however many episodes we're doing, we go through, we get our action, we do that step, we add the reward, we remember, we do that until we're done with the environment, we update the parameters of the agent, we keep track of all of this rewards, and then we go again. And then at the end, I plot these results, these average results. So now we can see, to get the action right, the policy, the softmax probability distribution gives us the distribution from which we can sample our actions. And so this policy function gives us the probabilities, so we just sample from them. To discount the rewards, we just go back, right, in time, and we consider a gamma here. And you can see that, you can see right here, like some potential problems with reinforce, right? The problem with this Monte Carlo sampling of this full episode length is that you might fail to attribute the correct cause and effect, right? If early on you could get a huge reward, you could say, hey, this action is a huge reward just because you got lucky and basically undid that action later and did really well. But that's just, I mean, that's reinforcement stuff that I can talk about more if you want, but I'm not going to for now. And then we just normalize them. And this removes them. This is no longer, right? Previously, the Monte Carlo sample of the rewards was an unbiased estimator. This is now no longer unbiased, but statistics, who even cares about that? Biased, unbiased, if it works, it works. And so now to update the parameters, we have our states, actions, and rewards that we're converting into these tensors. So now and this is using gradient tape with the TensorFlow Quantum. I've done that before, but always good to see more of it. So we get the distribution from the states. We get the action probabilities of our selected actions, keep in mind, not necessarily the most likely actions. We get the log probabilities by just doing the log. If this was a continuous distribution, these were mean and standard deviations instead of just a discrete policy distribution. We would probably just import TensorFlow probability and make them do the log calculations of a Gaussian. I mean, you can do that. I just wouldn't. And then we do the average error of the log probs times the reward batch. And so this is basically what, if I go back here, see if I can scroll up to it. Let's do here. Yeah, you can see this is, maybe I should scroll up here, right? This is the log probs times maybe, right? So we have the log of the policy times the returned. And this is the average, right? Oh, that's really bad. This is the average. And so we can see that we're taking the, oh my God, where's my, there it is. We can see that we're taking the derivative or the gradient with respect to this log probs, because the rewards is static and doesn't depend on the output of the model, and so it's just sort of a constant rather than any sort of derivative. So we get the gradients from this with this error, and then we can apply the gradients on the trainable variables and clear our memory. And so that's just the basic of reinforce. I just want to go over it maybe in more detail than I needed to, because it's kind of already assumes some background reinforcement learning. Now we can actually go into the policies. So we have two policies here, the re-uploading policy and the non-re-uploading policy, and they're both in this other file. You can see they're both right here. So here's the re-uploading policy. It's basically very similar to the code from the data re-uploading video, but we have some. So we establish our qubits, right? And I'm not entirely sure. I only tested this on cartpole, so I tried to make it flexible to environment, but it's possible that there was some implicit assumptions that I didn't even realize I was making, and so it might not work for all observation action spaces, but it does work for cartpole, I can tell you that. So we have our qubits that we set up, the number of parameters per like version of parameter. is there's 2, right, per layer, because there's 2 RYs and RZs per qubit. And then, so we get that number, we create the weights, right? So this is the standard weights, this is the re-uploading weights, and this is the weights for the output. So you can see this time it's a different shape, right? Because we're converting the shape of the output into the number of actions. And you can see I also initialize the input to be 1s just because they do it. So I'm just following the precedent. Total parameters, right? We have all of these and all of these. And so we just take the number of params times 2. We create the symbols for that. And the readout ops are just Z readout ops on Z basis on all the qubits. We create our controlled PQC, which has the circuit, the readout ops, and the adjoint differentiator. And then we have our generic input circuit and our standard beta value. And so I'm going to skip this for now. I'll come back to it. I'll explain why this is here. So we now make our circuit. We create an equal superposition to begin with. And then we go through layer by layer and put entangling and encoding layers so we can see that this is exactly as described in the paper. There's the RZ and RY gates entangled by controlled Z gates. And then the encoding is the RY and RZ in the opposite order. And yeah, that's pretty much it for the circuit. So now we're going to get to the forward, right? And you'll see, maybe I'll explain it now, right? So if we have, maybe if I go over to the drawing board, this will be easier to. So let's suppose, right, this is an implementation detail. So let's suppose we have our vector, right? So this is our first vector of weights, right? And this is our second vector of weights, right? These are just 2 vectors of weights, right? But if we want to alternate them, so we want, right, this is how our circuit goes. These are parametrized by this, by this, by this, by this, and so on, right? So these weights are being alternated. So when we call the function, right, we want, and we say, right, we're handing controlled PQC the weights. And we're saying, okay, I want to have these weights in this order, right? We have to give them in the same order that the parameters, the symbols are listed in. And so that would require us to have this section of weights down here, this section down here, right? So we're alternating it. And so this is where it might be a lot easier to follow their code, because what you can do is you can say, when you create the circuit, you can assign different symbols to the different weights, and then you can just sort the weights by the symbol names. And so then it's a lot easier. Well, maybe not easier, but a lot more, I don't know, general than what I'm doing. But what I have is I basically I say, okay, I know that we're going to alternate layers, right? And so all we have to do is I'm telling you the indices, and we'll see how this comes in so if we have this, if we concatenate them, right? So if we put the weights one after each other, so this is the total number of parameters, right? We want some of these, the first part of these, and then the first part of these, and the middle part of these, and the middle part of these, and so on, right? So that I can just say, hey, the indices that we want, that we can then gather later, are these alternating ones. So we gather some from the first set, and then we gather some from the second set, and then we go through repeatedly. And so this output, right, will look like, this will be 0, 1, 2, 3, 4. I'm just going to assume, right? Assume it's 4 weights per layer rather than 8, just so I can type faster. And then if we have like 10 layers, right, this will be 40. Oh, sorry. This will not be 40. If we have, no, it will. If we have 20 layers, it'll be 40, right? Because then this is the first index over here, right? So however long this is, maybe it'll be easier if I just do length of fees, right? This is the index, and then length of fees plus 1, right? This is what we're doing. And then we do that, and then we do plus 2, and then we do plus 3, and then we do 4, right? 5, 6, 7. and then we do plus length of fees plus 4, etc. Right? And so this will get us the order that we want. And so you'll see why I do that down here. So we have, once again, we get the input shape of the batch that we're calling it on. We repeat the inputs. And so this is a numerical value, right? These are the 4 numbers from cartpole that we're getting in this case. Or the batch of 32 by 4 maybe, or however large it is. And so, yeah, we have this, excuse me, we have this repeat that we're doing here just to repeat the inputs. And this is like the exact same from the re-uploading video. We tile the inputs so it matches the same size so they can be multiplied by the re-uploading weights. And then we do, in fact, multiply the re-upload weights, the self.lam, by the inputs. And so these are the actual parameters now that go into the circuit are multiplied. We reshape the standard layer weights. And then here's why we had the indices. We concatenate them together, and then we gather them, which means we reorder them basically in this indices order. And then we generate the output, which is 4 in the case of cartpole, the expected value of each of the computational z bases. And then we multiply the output by our output weight matrix, and then we do a softmax on these, and that's our representation, and that's our policy distribution. So we can see for the no re-upload policy, I do have lambda weights just because the way I encode the information is rather than uploading it every single time, right? Every single layer, I just do it on the first layer because obviously the information has to be shared somehow. And so I just do that in the first layer. But other than this is all the same. We don't have the indices because we don't need to gather them. We do this encoding before the entangling. Normally we did the entangling first, but basically we have to superposition and then we just input the data. And then we do all of this. This is the exact same. I copy this code exactly. And then this is also the exact same, except we don't have to tile them, right? We can just concatenate the fees after the lambdas because the lambdas are just the very first input weights. And then this is all the same down here. So this is just the same, but with no re-uploading. And then we can run it. And I'm not going to run it right now. You can see when I did run it. Let's see if I share this screen. No, this screen. No. Oh, right. I don't even have it shared. I did run it, and I'll show you the results. Just because even with adjoin, it takes a little bit, a few minutes sometimes to run, maybe more if it does well. So now I can. Let me just open all of the results at once. You can see my beautiful naming system. Okay, so before I do this, yeah, we can see. I want to make sure you know that the scales are different because I really should have done this all at once and normalized everything, but live and learn. So let's organize this one over here. So yeah, so this is what no re-uploading looks like. And this is far shorter. Remember, they did it for 2,000 iterations, but you know, I'm lazy, and so I only did it for 300. And so you can see the average reward of this without re-uploading gets to about 200. You can see, well, let me make sure. Yeah, you can see this gets to about 200. Here's an example that's a lot better, right? This one gets up to about 400. And so these are without re-uploading, and they're doing pretty well. These are with re-uploading. You can see the first time I ran it, and this is the same code. I didn't like bug fix anything. It didn't really learn. The second time, oh wow, that one didn't really learn either. But the third time did pretty well and got up to 400. So you can see the data re-uploading. I mean, this isn't a claim I'm making about the work or about this implementation even, because this implementation is not the work. I want to be very clear about that. I make no claims about what this says about anything. It's just useful information, perhaps. You can see it seems to be a little more brittle than the without re-uploading. But in general, re-uploading will probably be better, right, for more complex environments. But one thing I did want to show is we can just look. They have this comparison in the paper, I believe. Yeah, let's look. Let's go down to the graph somewhere. No, here we go. Fixed lambdas. No, that's not it. I could have sworn it was in here somewhere. Here, I think this is it. Reference. Oh, I guess they don't actually have it. They have fixed lambdas, which isn't really what we're interested in, right? This is it's not fixed, it's just not re-uploaded, but that doesn't really matter, I guess. So yeah, so we can see here that this is the results. You can average them, and you can see that, interestingly, to know re-uploading seems to perform better, but this is once again just an implementation. But what this really shows, and I guess I can actually say this, but this isn't unique to this work or any work. This is a common problem in my work. It's a common problem in everyone's RL work, is it is so very brittle. You know, I'm sure if I used their learning rates, I would get the exact same results that they do. Their code is available. It's transparent. But it's just one of those things where RL is just so brittle, and it can be such difficult. It'd be so difficult to re-implement. And so, yeah, these are the results for the paper that, that's not what I meant to have. For the paper, Variational Quantum Policies for Reinforcement Learning. I will link the paper, the code, and the TensorFlow Quantum tutorial below.